So, this is an important theorem called the Sigma-algebra monotone class theorem. It says, if A is an algebra of subsets of a set X, then the sigma-algebra generated by it is same as the monotone class generated by it. Just now we have all observed that M of so the first part we have already observed that M of A is a subset of S of A. For that one need not have even A as algebra. For any collection, M of C is contained in S of C. So, in particular, if A is an algebra, then M of A is a subset of S of A. So, we have to prove the second other way around inclusion, namely M of A includes S of A when A is an algebra. And to prove the other way around inclusion, let us observe it is enough to prove that M of A is an algebra, because why it is enough to prove this? Because, so let us observe enough to show M of A is an algebra will imply, because M of A is an algebra also a monotone class, and just now we proved every algebra which is a monotone class will imply M of A is a sigma algebra, because M of A is a monotone class, and if we are able to show it is an algebra, then it will be also a sigma algebra. But then we have A is inside M of A, and now if M of A is a sigma algebra, that will imply the smallest one must come inside it. So, S of A will be inside M of A. So, that will prove S of A is a subset of M of A and will be true. So, we have to only prove to show M of A is an algebra when A is an algebra. So, this is what we have to prove. So, let us start looking at a proof of this. So, first of all, to prove that M of A is an algebra, we should show that it is closed under complements, right. So, let us try to prove it is closed under complements. So, that means what? To show it is closed under complements, I have to show that for every subset in M of A, its complement is also in M of A. So, this is a technique which we are going to use very often. So, let us collect together all the sets B which have the property that whenever, so B is the collection of all those subsets, say that E complement belongs to M of A. So, to prove M of A is closed under complements, what we have to show is that M of A is a subset of B. So, M of A is a subset of B, we have to show that. So, let us try to prove that. So, claim, so let me repeat that we want to show that M of A is closed under the operation of complements. That is, A belonging to M of A should imply A complement belong to M of A. So, to show that, consider all those subsets. So, let us consider the collection B of all those subsets E contained in X such that E complement belongs to M of A. So, to prove this will be true. So, the required claim will be true. So, so this will be true if we can show M of A is contained in B. So, that is what we want to prove. We want to show, because then for every set A belonging to M of A, it will belong to B, that means its complement will belong to M of A. So, this is what we have to show. Now, let us observe, we are trying to show that M of A is inside a collection B, and what is M of A? M of A is the smallest monotone class including A. So, suppose we are able to show that A is inside B and B is a monotone class, then this claim will be true. So, for this enough to show. So, to prove this claim, it is enough to show one, that A is inside B, and second, we should show that M of and secondly, B is a monotone class, because once B is a monotone class including A, the smallest one will come inside. So, let us try to prove these two facts, that A is, so proof of 1 that A is a subset of B. So, let set A belong to A, that implies A is algebra. So, that implies a complement belongs to A, because A is algebra, and note implies a complement belongs to A, which is inside M of A, because A is always inside M of A. So, what we have shown, that if A belongs to A, then its complement belongs to M of A. Hence, that is same as saying that A belongs to the collection B. So, that means, so that is, so we have proved that B includes A. So, first property is true. Let us look at the second property. So, what is the second property we want to prove? The second property we want to prove is that B is a monotone class. So, let us take a collection A n, a sequence belonging to B, such that it is decreasing or increasing. So, let us say A n is increasing, okay. But A n belonging to B means what? That means what? A n complements belong to M of A, right. That is a definition of the class, B. So, saying that we have got a set A n in this, that means A n complements belong to A. Now, M of A is a monotone class. So, that implies that A n complements intersection will belong to M of A, provided we can say A n complements are decreasing, and that is true because A n's are increasing, because A n complements are decreasing, and M of A is a monotone class. So, that means this intersection belongs to it. So, that means union of A n's n equal to 1 to infinity, complement of this belongs to M of A. So, we have got whenever a sequence A n belongs to a bit and A n's are increasing, we have got the complement union, the complement of the union belongs to it. So, that means union of A n's n equal to 1 to infinity belongs to B. So, the collection B is closed under increasing unions, and let us finally prove that it is also closed under decreasing sequences. So, let us take a sequence of sets which is decreasing. So, let A n belong to B and A n's decrease. So, we want to show that the intersection of A n's belong to it, but A n's belong to B implies that just now we observed A n by definition A n complements belong to M of A. By definition A n belong to B means A n complements belong to A for every n, and that implies now A n complements is a sequence because A n's are decreasing, that is same as A n complements are increasing. So, union of A n complements belong to M of A, because M of A is a monotone class, and that implies that if the intersection of A n's n equal to 1 to infinity, okay, complement belongs to M of A. So, if whenever A n's belong to it and take the intersection of A n's, their complement belong to it, that means intersection of A n equal to 1 to infinity belongs to B. So, what we have shown is the collection B is closed under increasing union, is closed under decreasing intersections. That means, B is a monotone class. So, A is inside B, B is a monotone class, and that will prove that M of A is a subset of B, because so this is a monotone class including A. So, it must include the smallest one. So, that proves the first step of our claim, namely that the collection M of A is closed under complements. We wanted to show it is a algebra. So, what is the next step? Next step should be to show that M of A is closed under unions, right. So, that means, whenever two sets E and F belong to M of A, their union must belong to M of A. So, let us fix one of them. Let us fix the set F in M of A, and let us look at the collection L of F such that it is a collection of all those sets, so that A union F belongs to M of A. So, what we have to prove? So, in this we have to prove that M of A is closed under unions, we have to prove that M of A is a subset of L of F. So, once again the required property that M of A is closed under unions, we are translating into a property of a collection of subsets. So, let us try to show that M of A is contained in L of F. So, that is first we should try to show. So, to show that the collection M of A is closed under unions. So, this is what we want to show. So, let us fix a set F belonging to M of A and consider the collection which is, let us call it L of F. What is this collection? It is a collection of all those subsets in X such that E union F belongs to M of A. So, saying that M of A is closed under unions. So, to show, so we should show that M of A is a subset of L of F. So, that is what we should show. So, once again we want to show M of A is a subset of L of F. M of A is a monotone class generated by A, and we want to show it comes in under L of in some other collection L of F. So, that means, we should try to show that A is inside this collection, and this collection L of F is a monotone class. So, we should try to show that A is inside L of F for every F belonging to M of A, and second, L of F is a monotone class. Right. Let us just observe second one, which is quite obvious. So, let us observe L of F is a monotone class. So, for that what we have to show? Let us take a sequence E n belonging to L of F, E n's increasing, but that will mean if E n's are in L of F, that will imply that E n union F belongs to M of A. That is by definition of L of F, and M of A is a monotone class. E n's are increasing. So, E n union F is also increasing. So, implies that union of E n union F belongs to M of A. Because E n's are increasing, E n union F are increasing and belong, and that means it is same as saying that union of E n's union F belongs to M of A. And what does that mean? That means union of E n's belong to the class L of F. So, whenever E n's belong to L of F, E n is increasing, this implies that union E n's belong to L of F. So, this is what we have just now proved. A similar proof will work for decreasing also. So, saying that L of F is a monotone class is a straightforward argument, because M of A is a monotone class. Let us try to check that A is inside L of f for every f belonging to M of A. So, we want to check the first property, namely, so this is the property we want to check, that this collection algebra is inside L of f for every f belonging to M of A. Let us note, for the time being, we want to check this property for every f in M of A. Note, if f belongs to A, then for every E belonging to A, E union f belongs to A, because A is algebra. If E and f are two sets in A is algebra, that will mean that the union belongs to algebra, and that is included in M of A. So, what does this imply? This means, for every f in A, E union f belongs to M of A. That means, that the set E belongs to the collection L of f. So, once again, we are starting with a very simple observation. If a set f belongs to A and E belongs to A, then their union belongs to A, right, and A is always inside M of A. So, that means, E union f belongs to M of A, E union f belongs to M of A for every E belonging to A. That means, for every E belonging to A. So, that means, we have shown that A is inside L of f, right. So, now A is inside L of f, okay, for every f in A, implies L of f is a monotone class, just now proved, implies M of A is inside L of f for every f belonging to A. So, what we have shown is M of A is a subset of L of f for every f belonging to A, but we want to check that M of A is inside f for every f belonging to M of A. We have got only for f belonging to A. Now, here is a very simple observation which helps us. Note, a set E belongs to L of f if and only if f belongs to L of E. So, this is an observation which is going to be very important and very useful for us, that a set E belongs to L of f means what? E union f belongs to M of A, but if E union f belongs to M of A, that is same as f union E belongs to, that means, f belongs to L of E. So, saying that E belongs to L of f is same as f belongs to L of A. So, now let us translate this property. Okay. So, here it says M of A is inside L of f for every f belonging to A. Okay. So, that means, for every E belonging to M of A implies that E belongs to L of f, and that is if and only if f belongs to L of E, and here f was in the algebra, okay, f in the algebra. So, what we have got, for every f in the algebra, L it belongs to L of E whenever E belongs to L of A. So, that means what? That means, A is inside L of f for every f belonging to M of A. So, see how nicely we have turned the tables. Earlier we had M of A is inside L of f for every f in A. So, that means, every element here E is element in L of f, but here E belongs to L of f means f belongs to L of E. Now, f is in A, that means, A is in L of f for every f belonging to A, but that means, once that is true, now A is inside L of f for every f in M of A, and that implies that M of A is inside L of f for every f belonging to M of A. Because L of f is a monotone class, it includes the algebra A. So, it must include the smallest one. So, M of A is inside L of f for every f belonging to M of A. So, we have proved the required thing, namely M of A is inside L of f for every f belonging to M of A, and hence that means M of A is also closed under. So, here is what we wanted to prove. So, M of A is closed under unions, that we translated into the property that M of A is inside L of F for every f in M of A, and that we just now proved finally. And you see again and again we are, whenever we want to show something is true, we convert it into a property of a collection of objects and show generators come inside and everything comes inside. So, that proves that M of A is an algebra. M of A is a algebra. It is already a monotone class. So, it must be a sigma algebra, and S of A is a sigma algebra. So, that will prove that the required theorem. So, that proves this step proves the required theorem, namely. So, for this let us just go through this proof again. To show that M of A is closed under unions, we fix f in M of A and look at this collection, and we want to show M of A is inside L of F. For this we have to show that L of F is a monotone class, right, and A is inside L of F whenever f belongs to A. So, that says M of A will come inside for f belonging to A, and now reverse the roles of these two, that M of A for f in A, that means E belongs to L of F. So, f belongs to L of E, and reverse the roles, and that comes. So, that gives you the property that M of A is inside L of E. So, it is closed under unions, and hence it is a sigma algebra. So, it must include the smallest one, and that. So, that proves the fact that the sigma algebra generated by algebra is same as the monotone class generated by the algebra. So, let us just recall what have we done till now. We started with the set X, looked at a collection C of subsets C contained in P X. The first thing we looked at what is called a semi algebra. Then we looked at this collection C to be an algebra. Then we looked at this collection to be a sigma algebra, and then it to be a monotone class. So, a semi algebra, every algebra is a semi algebra, every sigma algebra is also an algebra, every sigma algebra is also a monotone class. So, this is something here. This way around implication may not be true, this way around implication may not be true, and this way around implication may not be true. And finally, we proved monotone class generated by an algebra is the sigma algebra generated by algebra if A is an algebra. So, that finishes our study of collections of subsets of X with special properties. I just want to leave you with some exercises which you should try, which are important. The first property or first exercise we would like to that whenever a collection is an algebra, it is equivalent to saying that empty set in the whole space, the collection is closed under complements, it is closed under unions, and that is equivalent to saying whether it is closed under complements because of this De Morgan laws. Another property, that whenever something is an algebra, a collection is algebra, it is also closed under symmetric differences, and any finite union in an algebra can be represented as a finite disjoint union whenever you are inside an algebra. That property we have seen, but you should try to prove this exercise yourself. Another property about semi algebras is you can, or sigma algebras, is that you can restrict. So, take a collection C of subsets of a set X and restrict it to a set E. That means, take intersection of all sets in C with E, then this is C restricted to E, and the property we want to prove is that if C is a semi algebra, then C intersection E is a semi algebra of subsets of E. And similarly, you prove the property that the algebra generated by the restricted sets is same as the algebra generated by generate the algebra and restrict. So, f of C intersection E is equivalent to f of C intersection E. So, you restrict and generate, it is same as generate and restrict, and the same property is true for algebras, is true for sigma algebras. So, that is the property about sigma algebras, and these exercises you should try to prove yourself. The steps are outlined here for you to prove. We have already proved these things in our lectures, but I will strongly advise that you prove these things yourself. And here is another example of generating new sigma algebras, semi algebras. F is a function from x to y. If you take sets in y and take inverse images, that gives you a collection of subsets of x. So, try to show that whenever if C is a collection of subsets of y, which is a semi algebra or a sigma algebra, then the pulled back sets also form a semi algebra or sigma algebra. Here is another example of take two collections of subsets f and g of two sets x and y. Look at the Cartesian products of these collections, show that in general it is not a algebra. Of course, if you take a collection of subsets f alpha, which are all algebras or sigma algebras, the corresponding intersection also is a algebra or a semi algebra. So, these properties unions may not be true. So, show that for union this property need not be true. So, that sigma algebra technique, that same thing is inside, then the generated sigma algebra comes inside, that we use. So, use that to prove that if you take the collection of all intervals in I and left open or right closed intervals, then the sigma algebra generated by all intervals is same as the sigma algebra generated by all left open right closed intervals and same as the Borel sigma algebra. So, I would strongly advise you to try these properties to get used to this concept of algebra, semi algebra, algebra, sigma algebra and monotone class. So, let us stop here today. Thank you very much.